Hello and welcome to Jeremy's IT Lab. This is the first video in the OSPF section of the course. In this video, we'll cover the basics of OSPF, how it works, basic configuration, and an overview of some of the topics we'll look at in this section. Because this course is focused on the ENCOR exam, we will of course focus on what you need to know for the exam. But throughout this section, I also want to help you develop your overall understanding of OSPF, so you can build a solid foundation for both the ENCOR exam and your future studies. This video will include lots of review from the CCNA, but we'll also dig deeper and cover some new details. Let's get started. First, let's begin with an overview of how OSPF works. OSPF is an open standard link state routing protocol. There are two versions in common use today. OSPF v2, which supports only IPv4, is defined in RFC 2328. This is what you learned in the CCNA. There is also OSPF v3, defined in RFC 5340. RFC 5340 specifically defines OSPF for IPv6, but OSPF v3 was later extended to support IPv4 as well. For most of this section, we'll focus on OSPF v2, and then cover version 3 and its differences with version 2 at the end. OSPF's operation can be broken down into 4 phases. First, routers will establish neighbor relationships and adjacencies with their directly connected neighbors via various OSPF message types. An adjacency is a neighbor with which the router proceeds to the next step, exchanging routing information to build the link state database, or LSDB. This is OSPF's topology table, which forms a map of the network topology. This routing information is exchanged via data structures called link state advertisements, LSAs. So the LSDB will look like this, with each router's LSA giving information about the router and its connected networks. All routers in an area must have identical LSDBs. So if all of these routers are in area 0, their LSDBs should all be the same. The CCNA focuses on single area OSPF, with all routers in one area like this. But for the ENCOR exam, you'll learn the basics of multi-area OSPF, which divides the network into a hierarchical design. Once these routers have built their LSDBs, the next step is calculating the best routes to each destination network using Dijkstra's shortest path first algorithm. And these routes are installed in OSPF's Routing Information Base, RIB, a database of the router's OSPF routes. And then those routes will be installed in the router's global RIB, in other words, the routing table, if there are no superior routes from other sources. For example, perhaps R1 selects the route via R2 to reach R4's LAN at 10.4.4.0/24. But one advantage of dynamic routing protocols like OSPF is not just their ability to automatically calculate routes in a stable network like this. They also have to be able to respond to changes in the network, such as new LANs being added, links going down or coming back up, etc. For example, if the R2-R4 link goes down for whatever reason, the routers will exchange updated LSAs over the remaining links so they can update their LSDBs, and R1 will calculate a new route to R4's LAN, via R3 this time. So this is how OSPF works at a high level. Everything we cover in this section of the course will address exactly how OSPF performs these tasks, how OSPF routers exchange the various message types to establish neighbors and adjacencies, how routers exchange routing information via the various LSA types, and much more. Now let's review the basics of configuring OSPF, enabling OSPF on interfaces. OSPF operates on interfaces where it's enabled, and there are 2 methods to do this. The first is in router config mode under the OSPF process. First, create the OSPF process with router OSPF, followed by the process ID, and then use the network command, which we'll look at in the next slide. The second method is to enable OSPF directly on each interface with IP OSPF, the process ID, area, and the area ID. Both methods achieve the same result. Notice that both methods specify a process ID. This process ID is locally significant. It just identifies the OSPF process on the local router. It's fairly rare, but a router can run multiple OSPF processes at once. If a router runs multiple OSPF processes, each process maintains a unique LSDB, and routes learned in one OSPF process aren't automatically shared between processes. To share routes between processes, you must configure redistribution. Redistribution isn't an ENCOR topic, but it's the process of sharing routes between different routing protocols or between different processes of the same routing protocol. All of the examples we look at will use a single OSPF process, so just remember that the process ID is locally significant. It doesn't have to match between routers for them to become OSPF neighbors. Now let's review the network command and look at a few details you probably didn't learn in your CCNA studies. The network command specifies a network address and a wildcard mask. Here's the command syntax again. I won't review how wildcard masks work again here, since you already learned that in the CCNA. Just remember that the network command doesn't directly specify prefixes to advertise. Instead, it matches interface IP addresses and activates OSPF on interfaces with a matching IP address. So it's very flexible. As long as the proper bits match between the network address in the command and the interface IP address, OSPF will be activated on the interface. My recommendation is to specify the interface's exact IP address with a /32 wildcard mask. That means you won't accidentally activate OSPF on an interface you don't want to. Let's look at an example on R1. First, I created the OSPF process with process ID 1. Here is the command to activate OSPF on G1. Network 10.1.2.1, 0.0.0.0, area 0. Once again, this doesn't mean advertise 10.1.2.1/32 into OSPF. It simply means activate OSPF on the interface whose IP address is 10.1.2.1. And here's the command for G2, once again specifying the exact IP address. Finally, I confirmed with show IP OSPF interface brief, and you can see the two interfaces. As a side note, the most recently activated interface will appear at the top of this list. Since I activated G2 second, it's at the top of the list. Now let's look at a couple of details about this command. First, if an interface is matched by multiple network commands, the most specific match takes precedence. Let me use R2 to show you what I mean. First, I activated OSPF on its G1 and G2 interfaces using the same approach as on R1, specifying each interface IP with a /32 wildcard mask. Then I configured another network command, network 10.2.4.0, 0.0.0.255, area 1. Both the second and third commands match G2's IP, 10.2.4.2, but each command specifies a different area number. Let's see which command takes precedence and determines the interface's area. As you can see here, the interface is in area 0. The 10.2.4.2/32 match is more specific than the 10.2.4.0/24 match, so G2 is placed in area 0, not area 1. If you specify each interface IP with a /32 wildcard mask, you won't encounter situations like this, but just keep this behavior in mind. Next, let's look at how the network command behaves with secondary addresses. First, if an interface has any secondary addresses, their networks will not be advertised unless they are matched by a network command. I'll use R3 to demonstrate. First, I configured secondary addresses on G1 and G2, 192.168.13.3 and 192.168.34.3. Then, I activated OSPF on G1's primary address with network 10.1.3.3 and a /32 wildcard mask. Now OSPF is activated on the interface, but how can we see which routes are actually being added to OSPF? One option is to view the OSPF rib. The command is show IP OSPF rib. I won't get into the details of this command in this video, but highlighted in green, you can see that G1's primary network, 10.1.3.0/24, is in the OSPF rib. But the secondary network, 192.168.13.0/24, is not. That's because there is no network command to match the secondary IP. Now let's change that. This time I configured network 192.168.13.3, matching G1's secondary address. Now the secondary network, 192.168.13.0/24, is added to the OSPF rib, and it is being advertised to R3's OSPF neighbors. So that's the first point about secondary addresses and the network command. Secondary networks will not be advertised unless they are matched by a network command. And one more point about secondary addresses. If a network statement matches a secondary address, but not the primary address, OSPF is not activated on the interface. Let's confirm with R3's G2 interface. I configured a network command specifying G2's secondary address, 192.168.34.3. In the output of show IP OSPF interface brief, you can see that OSPF is not activated on G2 yet. That's because there is no network statement matching the primary address. To fix that, I configured another network statement to match the primary IP, 10.3.4.3, and now OSPF is activated on the interface. So that's the second point. To activate OSPF on an interface using the network command, you must match the primary address, not just a secondary address. Now let's look at the other way to enable OSPF on interfaces. You already know this command from the CCNA. IP OSPF, the process ID, area, and the area ID. But let's look at a couple of details you might not know. I'll demonstrate on R4. First, I enabled OSPF on G1 with IP OSPF1 area 0. This command takes precedence over the network command for determining an interface's area. Let me demonstrate. On R4, I configured network 10.2.4.4 0.0.0.0 area 1, matching G1's IP address. So we have two conflicting commands, one specifying area 0 and the other area 1. Because the interface-specific command takes precedence, the interface remains in area 0, even after configuring the network command. So just remember that interface-specific configuration takes precedence over the network command. Next, let's look at how this command behaves regarding secondary addresses. By default, the IP OSPF area command will advertise all secondary networks on an interface. I'll use R4G2 to demonstrate. First, I configured 192.168.34.4/24 as its secondary IP address and enabled OSPF on the interface. To see which networks R4 is added to OSPF, I used show IP OSPF rib. Here you can see 10.3.4.0/24, G2's primary network. And here is 192.168.34.0/24, G2's secondary network. So as you can see, by default this command advertises any secondary networks in addition to the primary network. Now what if you don't want secondary networks to be advertised? You can add secondaries none to the command. Let's confirm using R4's loopback 0 interface. First, I configured 4.4.4.4/24 as a secondary address on the interface. Then, IP OSPF1 area 0 secondaries none, enabling OSPF on the interface without advertising secondary networks. And here is R4's OSPF rib. Only L0's primary network is added to OSPF. The secondary network was not. As a side note, let me point out that the loopback was added as 10.4.4.4/32, even though the net mask on the interface is /24. This is the default for loopback interfaces. They're advertised as /32 by default, regardless of the net mask configured on the interface. In a later video, I'll show you how to change that. Here are those points about enabling OSPF on interfaces we covered. I won't read them again, but I recommend taking notes. You should already know these commands from your CCNA studies, but hopefully you learned a couple of new points about how they work. And since we covered secondary addresses, note that OSPF adjacencies are formed using an interface's primary address, not its secondary addresses. That's because hello packets are sent from the primary address, not the secondary addresses. Secondary networks can be advertised in OSPF, but they are not used to form adjacencies. For the rest of this video, I removed those secondary addresses from the interfaces. Now let's review another very important point about OSPF, the router ID. Each router in an OSPF domain is identified by a unique router ID, or RID. It's very important that the RIDs are unique. If two or more routers have the same RID, OSPF operation can break. Or more accurately, it will break, so make sure the RIDs are unique. The RID is a 32-bit identifier that is often derived from an interface IP address. It's usually written like an IPv4 address, in dotted decimal notation, but it doesn't have to be a real interface IP address. You can use any arbitrary number as long as it's unique. The RID is automatically selected when the OSPF process starts, in the following order of priority. You should already know this. First, manual configuration with the router ID command takes precedence. If not manually configured, the highest IP address on an active loopback interface is selected as the RID. By active, I mean it has to be up. A disabled interface's IP won't be used. But note that OSPF doesn't have to be enabled on the interface for it to be selected. And if there are no active loopback interfaces with an IP address, the highest IP address on an active physical interface is selected. And once again, OSPF doesn't have to be enabled on the interface for it to be selected. If there are no active physical interfaces with an IP address, the router can't select a RID, and OSPF won't be able to start. Now let's see how this works. On R1, I checked its current RID with show IP OSPF. There are a few different commands you can use to view the RID. Show IP OSPF is just one of them. R1 doesn't have a loopback interface, so 10.1.3.1, its highest IP address on a physical interface, was selected. To change it, I configured router ID 1.1.1.1. Notice the message below. I have to reload the router or use clear IP OSPF process for the command to take effect. So I cleared the OSPF process, and R1's router ID is now 1.1.1.1. So you're probably used to this behavior. You need to reset OSPF for the new RID to take effect. Note the software version on R1, iOS XE version 17.03.08a. In older versions of iOS XE, like this, the router ID command doesn't take effect immediately if the router has an active adjacency. So we have to reset OSPF. But in newer versions, that's actually not the case. To test, I briefly replaced R4 with a router running IOL, iOS on Linux, which is available in CML. This runs a newer version of iOS XE. As you can see, the router ID is 4.4.4.4, which is the loopback address configured on R4, since I copied the config to this router. I then configured router ID 9.9.9.9. Let's see what happens next. This message is displayed. New router ID will take effect immediately. If OSPF adjacencies are up for OSPF 1, they will be reset. And here are those messages for the adjacencies going down. And without having to clear the OSPF process myself, the new RID takes effect immediately. Here's the version running on this router, 17.16.1a. As of iOS XE 17.13.1a, the router ID command always takes effect immediately, even if the router has an active adjacency. Don't worry about memorizing that version number or anything for the exam, but if you're configuring an OSPF network in production, be aware that on newer routers, this command takes effect immediately and will cause adjacencies to go down briefly. Next, let's briefly review passive interfaces. To demonstrate, I'll add a third interface to R1, G3 with IP address 10.1.1.1/24. An OSPF-enabled interface sends hello packets regularly to discover neighbors and maintain neighbor relationships. So R1 will regularly send hellos out of its interfaces like this, once every 10 seconds by default. This is critical for OSPF to function, but it's not ideal on interfaces with no OSPF neighbors for a couple of reasons. First, it adds unnecessary OSPF traffic. This is a minimal concern since the bandwidth and processing resources needed to send OSPF hellos is minimal, but it's still not ideal. The main concern is that an unauthorized device could form an OSPF adjacency and inject false routing information into the network. R1G3 doesn't connect to any routers, but as you can see in this output from debug IP OSPF hello, R1 still sends hellos from 10.1.1.1, which is G3. To fix this, we should configure G3 as a passive interface. A passive interface advertises its connected networks in OSPF, but doesn't send hellos and ignores any hellos it receives. There are two ways to configure it. The first is to use passive interface and then specify the interface. You could also use passive interface default to make all interfaces passive, and then no passive interface to re-enable hellos on specific interfaces. The effect is the same, but one method might be more efficient than the other, depending on whether you have lots of passive interfaces or just a few. To test, I configured passive interface G3 on R1. There are a couple of commands you can use to verify passive interfaces. One is show IP protocols. Under the OSPF section, there is a list of passive interfaces. Another option is show IP OSPF interface. If an interface is passive, it will say no hellos passive interface, like here. Now that G3 is passive, R1 will only send hellos out of G1 and G2, the interfaces that actually have OSPF neighbors. The other routers still learn about G3's network, but R1 doesn't send hellos out of that interface. One final clarification. You do not need to configure loopback interfaces as passive. Loopback interfaces never send hello packets, so making them passive doesn't provide any additional benefit. I think I may have said the opposite at some point in the past, but let me correct the record here. You can configure loopback interfaces as passive, but there's no benefit or need to do so. So you've enabled OSPF on the appropriate interfaces, and the routers made adjacencies and exchanged LSAs with each other. We'll cover how they do that in other videos. Now, how does a router calculate the best route to each of the destinations it has learned of? It uses a metric called cost. Each interface has an associated cost, and the total cost of a route is the sum of the outgoing interface costs along the path. So let's add some interface cost to this diagram to demonstrate. Both of R1's interfaces have a cost of 1. R2 G1's cost is 5, and G2's cost is 1, and same on R3. So what is the cost from R1 to R3's LAN? Well, R1 G2's cost is 1, R2 G2's cost is 1, and R3 G2's cost is also 1. So the total cost of the route is 3. What about the cost from R3 to R1's LAN? R3 G1's cost is 5, R2 G1's cost is 5, and R1 G1's cost is 1. So the total cost of the route is 11. As you can see, the cost is not necessarily symmetric if interface costs differ in each direction, as in the network below. But this is just an example. In reality, in most cases, both interfaces on a link should have the same cost, so we often refer to the cost of a link rather than the cost of each interface. I only show different costs here to demonstrate. Now let's look at how OSPF cost is calculated in iOS. RFC 2328 doesn't define a specific formula for calculating interface cost. Cisco iOS uses the following formula: reference bandwidth divided by interface bandwidth. And the default reference bandwidth is 100 megabits per second. You can modify this with autocost reference bandwidth. And you can also change an interface's bandwidth value with the bandwidth command. The bandwidth command doesn't actually change the speed at which an interface operates. It just affects the value that is used in the OSPF cost calculation. And you can also manually configure the cost of an interface with IP OSPF cost. But for now, let's focus on the autocost formula. As you can see here in the output of show IP OSPF, the default reference bandwidth is 100 megabits per second. To show the default cost of interfaces with various bandwidths, I modified the bandwidth values of these 6 interfaces from 10 megabits to 200 gigabits. Note that I edited the interface names in this output just to make it easier to understand. You can't actually change interface names like this. As I've highlighted, with the default setting, all interfaces with a bandwidth of 100 megabits or greater will have a cost of 1. That's because OSPF cost is an integer value. It doesn't support decimals, and any value less than 1 is treated as 1. So with a 1 gig interface, the formula gives 0.1, but it's treated as 1. And with a 10 gig interface, the formula gives 0.01, which is again treated as 1. This isn't ideal in modern networks, where speeds of 1 gigabit per second or greater are standard, as OSPF can't differentiate between links of different speeds. So let's try modifying the reference bandwidth and see how the results change. First, I set the reference bandwidth to 1000 megabits per second, or 1 gigabit, and then confirmed. Now, interfaces of 1 gig per second or higher have identical costs. Better, but still not ideal for many modern networks where 10 gig interfaces are fairly common. So next, I increased the reference bandwidth to 10 gigabits per second. This means that interfaces of 10 gigs or higher have identical costs. For many networks, this will be fine. 10 gigs is a common top speed, but let's increase it even more. Next, I increased the reference bandwidth to 100 gigabits per second. And here is the result. If you have some very fast links in your network, you might want a reference bandwidth of 100 gigs. Finally, to demonstrate one point, I set the reference bandwidth to 1 terabit per second. And here is the result. Notice that I've highlighted the cost of the 10 megabit interface, 65535. Given the formula, 1 terabit divided by 10 megabits should be 100,000. But interface cost is a 16-bit field, so the maximum value is 65535. These days, 10 megabit Ethernet links are quite rare, so you probably don't have to worry about it, just keep it in mind. And note that this maximum is only relevant to the cost of an individual interface. A route can have a much higher cumulative cost. Now let's move on to another major topic, multi-area OSPF. This will get its own video later in this section, but let me introduce it here. Larger OSPF networks are often divided into multiple areas. Area 0 is the backbone area, and all other areas must connect to Area 0, giving a two-tier hierarchical structure. So let's add some more routers here, R5 and R6. This is still a fairly small network, so single area would be fine, but let's make this Area 1. Now, what's the benefit of splitting a network into multiple areas? The main thing is scalability. Multi-area OSPF reduces LSDB size and also reduces shortest path first calculation workload. Let me show you what I mean by that. Let's say R4 on the right wants to send a packet to 172.16.5.0/24, R5's connected LAN on the left. R4 knows that packets to that subnet must go via R1, so the packet goes to R1, which forwards it to R5. Simple enough. But what if the link between R1 and R5, 172.16.15.0, goes down? That doesn't change things from R4's perspective. It still knows that to reach 172.16.5.0/24, the packets must go via R1. So once again, the packet goes to R1, and then R1, which is connected to Area 1, sends the packet via R6. R4 didn't have to calculate a new route to reach the 5.0 subnet. Routers in one area know about the prefixes in other areas, but do not have a complete map of those areas. This provides both of these benefits. It reduces the LSDB size of an area, and reduces SPF calculation workload. So let's see what Area 1 looks like from R4's perspective. R4 basically sees Area 1 like this, a collection of prefixes. When the R1-R5 link goes down, R4 knows that the 172.16.15.0 prefix isn't reachable anymore. But it doesn't have to use the SPF algorithm to calculate a new route to reach 172.16.5.0. The logic is still the same. To reach that prefix, the packets must go via R1, which will then forward the packets to the proper destination. Like this, instabilities in one area are hidden from other areas. If the R1-R5 link is flapping up and down, the impact on R2, R3, and R4 in Area 0 is minimal. They don't have to recalculate routes each time. And this hierarchical design also provides an opportunity for summarization. Area border routers, ABRs like R1, can perform summarization between areas. So instead of R2, R3, and R4 knowing about each individual prefix in Area 1, R1 can summarize the area as 172.16.0.0/16 and advertise that summary into Area 0. And it can summarize Area 0 as well. Here are those prefixes between the routers again, all beginning with 10. So R1 can summarize Area 0 as 10.0.0.0/8 and advertise that summary into Area 1. So R5 and R6 don't know about each prefix contained in Area 0. They just know the 10.0.0.0/8 summary that R1 advertises. Summarization like this further reduces the LSDB size of each area and hides instabilities in one area from other areas. We'll cover more information about the benefits of multi-area OSPF and summarization later in this section of the course. Multi-area OSPF leads well into the next topic, classifying routers. RFC 2328 defines 4 router roles or types. First, internal routers have all OSPF-enabled interfaces in the same area. In the network below, that includes R2, 3, 4, 5, and 6. R4G3 is outside of Area 0, but it's not OSPF-enabled, so R4 still counts as an internal router. Only R1 is not an internal router because it has interfaces in 2 areas, Area 0 and Area 1. Instead, R1 is the next type of router, Area Border Router, ABR. An ABR has interfaces in multiple areas, like R1. Backbone routers have at least one interface in area 0, the backbone area. In this network, that's R1, R2, R3, and R4, all connected to area 0. And then we have Autonomous System Boundary Routers, ASBRs, which advertise routes from outside the OSPF domain into OSPF. Currently, we don't have any ASBRs, so let's add an internet connection to R4. R4 likely has a default route pointing to the internet, and it can advertise that route into the OSPF domain, making it an ASBR. Other examples include routers redistributing routes from another protocol, like EIGRP or BGP, into OSPF. Redistribution isn't on the ENCOR exam, so we won't cover it in this course, but it's definitely something you'll learn if you continue your studies beyond ENCOR. So those are the 4 router roles: internal router, ABR, backbone router, and ASBR. Note that these roles are not mutually exclusive. For example, look at R4. All of its OSPF-enabled interfaces are in area 0, so it's an internal router, and also a backbone router. And since it advertises its default route to other OSPF routers, it's also an ASBR. Now let's review how we can configure R4 to advertise a default route into OSPF. The basic command is default information originate in router config mode. And you would typically configure it on the router that has internet or external connectivity, which is R4 in this network. You already know this command from the CCNA, but let's look at a few more details. By default, the router must have a default route in its routing table to advertise a default route into OSPF. So if we don't configure a default route on R4, it won't advertise one even if we configure default information originate. But you can add the always keyword to the command to advertise a default route even if the router doesn't have its own default route. So the command becomes default information originate always. And by default, the advertised route will have an OSPF metric of 1 and a metric type of E2. We'll see what the metric type means in the next slide. But you can modify these defaults by adding the metric and metric type options to the command. The metric type can either be 1 or 2. Again, we'll test this later. First, let's test the basic command. I configured a default route to the internet on R4. Then I used the basic command, default information originate. Let's see how the route appears on R5. Here it is in the routing table. As I've highlighted, the metric type is E2 and the metric is 1. Now let's look at the different route types in OSPF to see what this E2 actually means. There are 3 main types of OSPF routes: intra-area, inter-area, and external. Let's review them. Intra-area routes are routes to destinations in the same OSPF area as the local router. These appear as O routes in the routing table. Then, inter-area routes are routes to destinations in a different OSPF area, and they appear as OIA routes in the routing table. And finally, there are external routes, which are routes to destinations outside of the OSPF domain. This is where the E2 metric type in the previous slide is relevant. Type 1 external routes include the external metric and the cost to reach the ASBR advertising the route, and appear as OE1 in the routing table. And then Type 2 external routes include only the external metric, appearing as OE2 in the routing table. Now let's take a look at R5's routing table to see these different route types. Here is R5's routing table. First, at the top, you can see the default route from R4 with the route type OE2, a Type 2 external route. Because the route type is E2, only the external metric of 1 is included. The cost for R5 to actually reach R4 isn't included in the routes metric. Then below that, we have some inter-area routes to networks in Area 0, the links between R1, R2, R3, and R4. And finally, a couple of intra-area routes to the R1, R6 link using ECMP, Equal Cost Multipath. Because R5 is directly connected to the other networks in Area 1, those routes don't appear as OSPF routes in the routing table. So here you can see all 3 of the major route types: intra-area, inter-area, and external. To finish up, let's check out the other external route type, Type 1. On R4, I changed the default information originate command, adding metric 10 and metric type 1. Before we look at R5's routing table again, what do you think the cost of R5's default route will be now? Type 1 external routes include both the external metric 10 in this case, and the cost to reach the ASBR. All of these links have the default cost of 1. So that's 1 to go from R5 to R1, 1 to go from R1 to R2 or R3, and then 1 to go to R4. Therefore, the cost of R5's default route is now 13. So remember the difference between external Type 1 and Type 2 routes. Type 1 includes both the external metric and the cost to reach the ASBR, while Type 2 includes only the external metric. Finally, let's review what we covered. We looked at quite a few topics in this video: enabling OSPF on interfaces, the router ID, passive interfaces, OSPF cost, multi-area OSPF, router types, default route advertisement, and route types. There's no way to fit everything on one slide, but here are some of the important points. Much of this is review from the CCNA, but we also looked at several new details that I didn't cover in my CCNA course, so hopefully you picked up something new. Finally, let's do a short quiz to test your understanding of these topics. Here's quiz question 1. R1 is connected to OSPF areas 0 and 1 and advertises a default route into the OSPF domain. Which of the following router roles apply to R1? Select all correct answers. Pause the video now to think about your answers. Okay, the answers are A, C, and D. A is correct because R1 connects to multiple OSPF areas, making it an area border router. C is correct because it connects to area 0, the backbone area. And D is correct because it advertises a default route to the internet into OSPF, making it an autonomous system boundary router. B is incorrect because an internal router connects only to a single OSPF area, so a router can't be both an ABR and an internal router. Aside from that, these roles are not mutually exclusive. A router can be an ABR, a backbone router, and an ASBR at the same time. Here's quiz question 2. Which of the following statements about the default information originate command are true? Select 3. Pause the video now to think about your answers. Okay, the answers are A, C, and F. A is correct because the advertised route has a default external metric of 1, although you can modify that by adding the metric option to the command. C is correct because if you don't specify the always keyword in the command, the router must have its own default route before it advertises one into OSPF. And F is correct because the advertised default route uses metric type 2 by default. External routes can use metric type 1 or 2, and 2 is the default for this command. And that means B is incorrect, because OE1 is for an external route using metric type 1. The default for this command is OE2. D is incorrect because intra-area routes are to destinations within the same OSPF area. This command injects an external route, not an intra-area route. And it's also not an inter-area route, so E is incorrect. Inter-area routes are to destinations in another OSPF area, but this command advertises an external route. Here's quiz question 3. Which of the following statements about the network command are true? Select 2. Pause the video now to think about your answers. Okay, the answers are B and D. B is correct because if you configure multiple network commands that match the same interface, the most specific command takes precedence to determine the interface's area. And D is correct because the command works by matching against IP addresses. If a match is found, OSPF is enabled on the interface. A is incorrect because the command doesn't directly specify prefixes to advertise. It is just used to enable OSPF on interfaces. C is incorrect because secondary networks are not automatically advertised, unless there is a network command that matches the interface's secondary IP addresses. And E is incorrect because OSPF won't be activated if only a secondary address is matched. The command must match the primary address to activate OSPF. Okay, that's all for the quiz. And that's all for this video on OSPF basics. We looked at several concepts you already learned in the CCNA, but also dug deeper and covered some more details. In the following videos of this section, we'll dig even deeper into topics like OSPF messages, network types, LSA types, route summarization and filtering, and more. I hope this video was helpful. Thanks for watching. Before we wrap up, I want to say a quick thank you to the channel members whose names you see on screen. Your monthly support helps me keep making these videos and keep this content free for everyone on YouTube. I really appreciate it. Thank you for your support. If the video was helpful and you want to support me, click the join button under the video. And please subscribe and like the video. It really helps me grow the channel and keep making these videos for you all. Thanks again.